Alright guys, we're going to take a look at more slope stuff. So yesterday or previous video, I guess we did a little bit on slope. So slope is rise over run. You look at a line, you look at how it moves from left to right. So these guys here were going up. C to D was going up, so that is a positive slope. It has a rise of 1, 2, 3. So we go up 3. We're going up 3 here. You know what, let me get my writing pad a little closer to me. Almost dropped the computer. That would have been loud. And then I go over. That's my rise. Would be up 3, and then I go over 1, 2, 3, 4, 5, 6. So I have a rise of plus 3 and a run of plus 6. So my runs are always going to be positive. I'm always going this way. And my rise will be positive if I go up. If I went down, it'd be negative. I'd have a negative slope, something like this. Okay, and then 3 over 6 in lowest terms is 1/2. So my slope would be plus 1/2. All right, so that is slope. And now we're going to look at slope as a rate of change. So we're just going to do some word problems and real life situations, I guess. So rate of change is Greek delta. Looks like a triangle. It is a triangle. So it's the change in one quantity relative to the change in another quantity. So that's the rate of change. Okay, and it's expressed as a ratio. And it requires units. So in these questions here, it's not x, y. It's going to be things like this. You travel this far in this amount of time. How fast are you going? 288 kilometers in 3 hours. Divide 96 kilometers per hour. Okay. So when you do questions like this, just make sure that you keep your rate here and your units, sorry. And the units will always be the unit of the top over the unit of the bottom variable. Okay, so up top here, you're going to always have here. This is always going to be. I'm just going to keep with this dependent over independent. Okay, so on the bottom you're going to have your independent. On the top you're going to have your dependent. So here I print 45 pages in 5 minutes. So 45 are the pages. Okay, so I start printing, and I print, and I print, and I print, and I print for 5 minutes. So my independent is how long I print for. My dependent is how many pages come out, depending on how long I printed for. So 45 pages divided by 5 minutes, that gets me 9 pages per minute. So that's 9 pages per minute, and I use that as a ratio. When you look at things, you can also have a negative rate of change. Okay, so here if your line is going to come down, then you'll have something that will give you again, let's go back to what we had before, a negative rise, so you're coming down, and a positive run will get you a negative rate of change. So these questions we went over in class. You have your rise over your run, again your delta y, your change in your dependent, okay, or your delta dependent over your delta independent. So here we just take these here and we say, well, what's the change here? Well, the change between here and here is going to be $1.50, and that's going to be 30 on the bottom. Why did I use this and this? So I used this guy and this guy, so I went from here to here to get my rate of change. I could have used anything. I could have used these two. So here I could have said my rate of change is going to be my, 5 subtract 0. Sorry, let me do that. My rate of change will be my change in the dependent variable. So I could have said the change here is that it goes up a quarter. It goes from 250 to 275, and it does that while this goes up 5. So how do you get these numbers? You say this subtract this, or this and this subtract this. Okay, so this is the top, this is the bottom. You get your top part here, your dependent, the change in the dependent over the change in the independent. Okay, and then keep your units. That's dollars per year. And then if I'd worked this out, I would have got the same number that I got below here. So I get 5 cents or $0.05 per year change. Okay, so it doesn't matter which points you use if you have a straight line, which we'll be doing only straight lines in this course. So your rate of change works that way. That means the slope is the meaning of the slope is dollars per year. Therefore, the change in dollars per year, in this case, about the cost of a hot dog. So a hot dog goes up 5 cents a year in cost. Inflation. What are you going to do? or any equation that represents the cost. Okay, so if we're going to look at this, what you're going to do is you're going to start off here with your initial cost, and you're going to add to it the rate of change. Okay, so in this case, we have y represent the years since 1980. We're going to say that the cost is 250 plus this. So let's go back to what we were talking about yesterday. Because it's just because it has this thing here. If we graph this, it won't go through the origin, which makes this a partial variation. Okay, so let's go back to remember we had partial and full variation, partial variation or direct variation. Sorry, full or direct variation. Partial variation doesn't go through the origin. It has something plus something times something, and that's what we had here. Okay. We look at something called first differences as a rate of change. So all these are going to get us to the slope. So this is the slope of our line again. So the rate of change here, if we got the slope again, so if I went slope, what's the slope? I go up. My rise is from here to here. My rise would be in the right units would be 2.5 or 1.5. Sorry. So here's my rise of 1.5. I go from 2.5 to 4. That's up 1.5. And my run here would be 30. So my rise over my run is the 1.5 over 30. There's my slope. Okay, but the only difference between this and what we were doing earlier is that this has units. So these numbers won't be the same on the bottom. We're not going over 1 each time. We're not going up 1 each time. We're going over whatever the units are on the graph. So rise over run, slope, rate of change, they're all the same thing. Okay, and the last thing we're going to look at is first differences. They're also the same. First differences are not quite the same if the x value in the x values in this column don't raise by 1. So let me just show what I'm looking at here. What I'm saying is this guy here, this column, I have x and I have y. I have my independent and my dependent. This guy here is going up by 1 each time, 0, 1, 2, 3, 4. This one here will go up by something else. Okay, and if you're going up by 1 here, what you're saying is for each time I go over 1, I'm going down 4. I went from 7 to minus 3. So if I was to graph this, I go over 1, down 4. Over 1, down, oh sorry, that's 0, 7. So 0, 7 will be up here. And then I go to 1, 3, which is down here. So I went over 1, down 4. Then I'm going to 2 and down 4 to negative 1. So I get to the point 2, negative 1. So these all have a first difference of minus 4. How do you get that? You take this value, and you subtract that value, or you ask yourself in your head, how do I go from 7 to 3, minus 4? How do I go from 3 to minus 1, minus 4? Every time you have a straight line, your first differences will be the same. Later on, when you get to grade 10, this will be your test for, is it a linear equation? Is it a straight line? Do I have the same first differences? Okay. These first differences here are not the same. Okay, so this will not be a straight line. It's not because these numbers are growing in a weird fashion. It's that when you do the first differences, I go up plus 2, I go up plus 2, I go up plus 6, I go up plus 1. You graph that, it's going to be something. What is it? It's just a weird shape. But in general, it doesn't matter what it is. As long as it's not a line, then it's not linear. Okay? So first differences are the same. Linear relation between two variables that appear as a straight line when graphed has first differences that are equal. This is the whole course on straight lines, linear relationships. Okay? They have the same slope. So we've been graphing these guys. One test is to see if we have a first differences that are the same. They're the same, it's linear. And how do they look like in equations? What you're looking for is you have y equals something times x. Y equals 3x, 3x plus 6, 5x, y equals 5x, y equals negative 5x, y equals negative 1/5 x, minus 6. It doesn't matter as long as you have an x. You don't have an x squared, you don't have an xy, you don't have an x cubed, you don't have a whatever, okay? You have x in that case, okay? Linear, straight, line, first difference is equal, first degree is 1, back to degree, you have x, so you look here and you say, what's the exponent on this guy? It's 1, remember back we went to, we're talking about degrees of equations. The degree of this equation is 1, that is a linear relationship. Modeling with graphs, we're going to graph now, real quick. You just take these points here and you graph them, and if you graph them and you look at the first differences are the same in lines. Now this is not the slope because you're not going up by 1 here. Okay? If you change by 1 here, this guy's your slope. Okay? So what you do here is if you're going up by 1 each time, your slope here is obvious, minus 4, minus 4. Your rise is minus 4. your run is 1. Your rise is -4, your run is 1. Here your rise is 2, but your run isn't 1. So here you would have a rise of 2. If you wanted to look at the slope of this, I'm going to jump ahead. There's 2. This guy's going down, this guy's going up 3. That'd be 2/3. Okay, so be careful. This isn't necessarily your slope. It's only your slope when this goes up by 1. If this column is going up by something other than 1, then you have to take the first difference and divide by how this guy is changing. So let's go over here. Here we're going up by consistent first difference. We have 1, 1, 1, 1, 1. So it's linear for sure, but this is not, the x column is not going up by 1. This is going up by 5, so my slope would be 1/5. Okay, I don't want to get things too complicated. They're all linear, but they're not necessarily slopes equal to the first differences. Depends on the table. Okay, and then we can just put it all together here. Here's the situation. Do we have partial variation, direct variation? You graph this guy. If it goes through here, it's partial. Or sorry, it's direct. I knew I was going to mess it up. I just knew it. I'm just getting old. I think something, I say to myself, don't say it, and then I say it all the time. That's a sign of getting old. I guarantee it. Also, less hair on my head, too. That's also another sign. Anyway, calculate the slope. Slope, okay, so again, let's calculate the slope. If we were to get the slope off here, we'd do our rise over run. 1, 2, 3, 4. That's my rise. That's my run. It's positive, so it'd be 4/3. But let's go over here. Here's my first differences. There's 4 as my first differences from the table. But remember what I said. If this doesn't go up by 1, then what you'll have to do is divide by 3. So I have plus 4/3 as my slope here. Okay? Either way you want to do it, that's how you get slope. Just be careful over here that this is not your slope. I said that 1,000 times. Again, another sign of being old. How does the slope relate to the first differences? They're close, okay? But they have to divide by the y here. Last thing I want to show you is using coordinates to find slope. So this guy here is the way you're going to do it in the long run. If you don't have the graph, if you have the graph, that's great. You can do rise over run. But if I just give you 2 points, let's say -4/10 and 1/9. So here, this is -4/10. So if we want to look at this here, the point is -4 and 10. This one is 1, 9. So here I can come and say, okay, well, what's my rise? My rise is -1, and my run is 1, 2, 3, 4, 5. So I got -1/5. That would be my slope if I did rise over run. But a kind of a cumbersome way to do it, but a way to do it without graphing is to take the coordinates of one point and subtract them from the coordinates for the other. So what we do here is we have slope, which we call m, is our rise over run, and we call that the change in y over change in x, which is delta y over delta x. But another way to talk about it is to say that it's the coordinates, it's y2 minus y1 over x2 minus x1. So what I'm saying here is you take 1 point and you have the coordinates, the y and the x values from point number 2, and you subtract from them the y and x coordinates of point number 1. So I just made that confusing. Let's call this point 1 and point 2. Here, this is my x and my y. A way to get the slope is to say, we're going to take this guy and subtract that from him for the top. So how much do I change in rise? Okay, that's my y coordinates. So I go 9 subtract 10. 9 subtract 10 is -1. So that's 9 subtract 10 is -1. And then 1 subtract -4. This is where we have to be careful. 1 subtract -4. 2 negatives become a positive. 1 plus 4 is 5. I have a slope of -1/5. So that is getting slope by using points. Okay. So here, let me do that again for 2 different points. I end up here, rise 1, 2, 3, run 1, 2, 3, 4, 5, 6. I'm going to have a slope of 3/6, which is a half. So that's from the graph, but now I'm going to do it with the coordinates of the points. Here, I'm going to call this point 1 and point 2. I go 5 subtract 2 on top here. So these are my y values. 5 subtract 2, I get 3. 6 subtract 0, I get 6, equals 3/6, 1/2 in lowest terms. Okay. If I change that order, it doesn't matter. Okay. I can come back and I could have said, why don't I make this point 1 and this point 2? And if I did that, what I would do is I would go 2 subtract 5 on top, which is -3. And on the bottom, I would go 0 subtract 6, which is -6. two negatives become a positive, lowest term is 1/2. Okay, so that's getting slope from the coordinates without graphing, but it all works together. I hope I've been drilling this through your head and you've been noticing this. Okay, slope, first differences, not necessarily first difference is divided by the y difference, delta y over delta x, rise over run, change in y over change in x. All this is the same thing. This is your slope, and later we're going to call that m. Okay, hope that went well.